On October 9, 2022, multiple gamma-ray satellites orbiting Earth had their detectors driven off scale at the same time. Not a malfunction, not a software error. A single flash of light from 2.4 billion light-years away had saturated instruments designed to measure the most energetic radiation in the universe. Astronomers called it the brightest of all time, the BOAT. It measurably disturbed Earth's ionosphere from 2.5 billion light-years away. But here is the part that nobody expected. That flash, as powerful as it was, is not even close to the largest explosion since the Big Bang. That record belongs to something far more unsettling, and it left a wound across space that you could fit 15 Milky Way galaxies inside. When astronomers say the largest explosion since the Big Bang, they are not being poetic. They mean it literally. They mean a single event, a discrete moment of violence, that released more energy than anything else the universe has produced in 13.8 billion years. But the answer to which event holds that record depends on a question most people never think to ask. What do you actually mean by largest? The brightest flash? The most total energy? The most destructive aftermath? Because each of those questions points to a completely different object. And over the last 5 years, astronomers have discovered that the universe is capable of violence on scales that did not fit inside any existing category. They had to invent a new one. This is the story of 4 explosions. Each one broke a record. Each one was supposed to be impossible. And together, they redraw the map of the most extreme physics in the observable universe. Start with the BOAT GRB2210009A, the brightest burst of gamma-ray light any human instrument has ever recorded. It arrived on October 9, 2022. A pulse of gamma radiation so intense it saturated the detectors on NASA's Fermi Space Telescope for several minutes. Think about what that means. A telescope designed specifically to measure the most energetic light in the universe could not handle what it was seeing. The signal was off the scale. The source was a collapsing star, 2.4 billion light-years away. In its final moments, the star's core gave way and formed a black hole. And as it did, 2 jets of material erupted in opposite directions, moving at 99.99% of the speed of light. One of those jets happened to be aimed almost directly at Earth. That jet carried gamma rays across 2.5 billion light-years of empty space. And when they arrived, they did something that should make you pause. They measurably altered the ionosphere, the electrically charged layer of atmosphere roughly 80 kilometers above your head. Instruments in Germany and India detected the perturbation. An event from before multicellular life existed on this planet reached across the universe and left a detectable imprint on our upper atmosphere. On paper, the BOAT released what appears to be around 10 to the power of 55 ergs of energy in its raw calculation. That is roughly 10,000 times the total energy our sun will produce across its entire 10 billion-year lifetime, released in a few hundred seconds. More energy in 5 minutes than our star will generate from birth to death. But there is a catch. Gamma-ray bursts are not explosions in the way you might picture them. They are beams. Tight, narrow jets, only a few degrees wide, screaming outward from a single point. When astronomers calculate the energy of a GRB, they initially assume the energy went out equally in all directions. That gives you the isotropic equivalent. But when you correct for the beaming, when you account for the fact that all that energy was concentrated into a narrow cone, the true total energy drops dramatically. From 10 to the power of 55 down to something closer to 10 to the power of 50 or 51. Still enormous, but no longer record-breaking. The BOAT was the brightest flash, not the most energetic event. It was a spotlight, not a bomb. So what happens when the universe builds a bomb? In 2023, a team led by Philip Wiseman published a study in the monthly notices of the Royal Astronomical Society about an object they had found hiding in survey data. It had been glowing for more than 3 years. Not a quick flash like a gamma-ray burst. A slow, sustained, relentless outpouring of energy, 8 billion light-years away. They called it a T2021 LWX. The internet gave it a better name: Scary Barbie. Scary Barbie was not a collapsing star. It was not a supernova. It was something different. A supermassive black hole at the center of a distant galaxy had captured a star and was tearing it apart. Not quickly, the way a small black hole might shred a passing object. Slowly, methodically, over years. The star's material spiraled inward, heated to extreme temperatures, and radiated energy outward in every direction. Not in a beam, in all directions at once. Total energy output was roughly 1.5 times 10 to the power of 53 ergs. That is more than 25 times the energy of the most powerful supernova ever recorded. And unlike the boat, this number does not need a beaming correction. Every direction got the full dose. Scary Barbie was a member of what scientists were just beginning to recognize as a new class of event. But it would take 2 more years and 2 more discoveries before that class got its name. In June of 2025, Jason Hinkle and his team published a paper in Science Advances that changed the field. They had studied 3 of these ultra-powerful long-duration events side by side. Each involved a supermassive black hole, at least 100 million times the mass of our Sun, devouring a star at least 3 times more massive than our Sun. Each released between 1/2 and 2.5 times 10 to the 53 ergs. Each lasted for months, sometimes years. Hinkle gave the class a name: Extreme Nuclear Transients, ENTs. And then, just 5 months later, the class got its most extreme member. In November of 2025, Matthew Graham at Caltech published a study in Nature Astronomy describing something that had been lurking in survey data since 2018. A flare so luminous it outshone 10 trillion suns at its peak, 30 times brighter than any previous black hole flare ever recorded. The black hole responsible was 500 million times more massive than our Sun, and it was consuming a star at least 30 times the mass of our Sun. Astronomers nicknamed it Superman, and the lead researcher described what was happening in terms that are difficult to forget. The star, he said, was like a fish only halfway down the whale's gullet. The flare was still ongoing. The black hole was still feeding. 10 billion light-years away, right now, a star is being slowly torn apart, and the light from that destruction is bright enough to outshine an entire galaxy by a factor of 10 trillion. If that number surprised you, hit like. It surprised the astronomers too. Superman was not just a record. It was, in Graham's words, roughly a 1 in a million event among active galaxies. It put itself into its own category. If you have been following our series on cosmic extremes, subscribe. This is video 5, and they keep getting stranger. But Superman, as extraordinary as it is a transient, a single event. A black hole eating a single star, no matter how violently, will eventually finish. The star will be consumed, the light will fade, and then the black hole will sit quietly, waiting for the next meal. What if the explosion never really stopped? 390 million light-years from Earth in the constellation Ophiuchus, there is a galaxy cluster. Thousands of galaxies held together by gravity are surrounded by a vast cloud of superheated gas called the intracluster medium. This gas is so hot that it glows in X-rays. In 2016, astronomers using NASA's Chandra X-ray Observatory noticed something strange in the data: a dent in the gas, a region where the hot gas was simply missing. They measured it. The cavity was enormous. When they calculated how much energy it would take to carve a hole that size and gas that hot, the number was so large they assumed they had made a mistake. They published cautiously and moved on. 4 years later, Simona Giattantucci at the Naval Research Laboratory and her team went back. This time, they looked with radio telescopes, the Murchison Wide Field Array in Australia and the Giant Meter Wave Radio Telescope in India. What they found filled the cavity perfectly, Radio emissions, the fossil glow of particles that had been blasted outward by jets from the supermassive black hole at the center of the cluster. The radio data, Giacontucci's colleague Maxim Markovich said, fit inside the X-rays like a hand in a glove. The cavity was real. The eruption had happened, and the scale was beyond anything previously recorded. The hole in the gas is 1.5 million light-years across. Let that land for a moment. Our entire Milky Way galaxy is about 100,000 light-years across. You could line up 15 Milky Way galaxies, edge to edge, and they would just barely fill the wound that this single eruption carved into space. The edges of the cavity still glow in radio light, a fossil imprint of particles blasted outward at tremendous speed, still ringing from the impact millions of years later. Giacontucci compared it to the eruption of Mount St. Helens, the 1980 volcanic blast that tore the top off a mountain. The difference, she said, is that you could fit 15 Milky Way galaxies in a row into the crater this eruption punched into the cluster's hot gas. Think about that for a second. Not a star exploding, not even a galaxy dying. A single black hole at the center of a single galaxy carved a scar across a structure that contains thousands of galaxies. The total energy required was an estimated 5 × 10 to the 61 ergs. To put that in perspective, the raw isotropic estimate for BOAT was 10 to the power of 55. The Ophiuchus eruption released roughly 1 million times more energy. Superman, Scary Barbie, every ENT ever recorded, all of them combined are a rounding error compared to what happened in Ophiuchus. But here is the critical distinction, and the reason this story is more complicated than a simple ranking. The Ophiuchus eruption was not a flash. It was not a transient. It was not over in months or years. It was an AGN outburst driven by a supermassive black hole that fed continuously over millions of years, channeling matter into jets that slowly, relentlessly inflated a bubble in the surrounding gas until it reached a scale that dwarfs galaxies. The BOAT lasted seconds. Superman has lasted years. Ophiuchus lasted longer than our entire species has existed. It is the single most energetic discrete event ever recorded in the universe since the Big Bang. But it unfolded over timescales that dwarf human comprehension, millions of years of continuous feeding. No telescope watched it happen in real time. We found the scar and worked backward, the same way geologists reconstruct an ancient volcanic eruption from the crater it left behind. One final detail most accounts leave out. The eruption has stopped. The black hole went quiet. The Chandra data shows that the densest, coolest gas in the cluster has shifted away from the central galaxy. It drifted, sloshing like wine in a tilted glass, probably set in motion by the eruption itself. And once the gas moved away, the black hole lost its fuel supply. The jets shut down. The engine went silent. The most powerful explosion since the Big Bang turned itself off. So, which is the largest explosion since the Big Bang? The answer depends on what question you are asking. If you mean the brightest flash of light, it is the BOAT, a gamma-ray burst so intense it saturated satellites and disturbed our ionosphere from across the observable universe. A once-in-10,000 years event that we were lucky enough to catch. If you mean the most luminous ongoing event, it is Superman, a black hole consuming a star 30 times more massive than our sun, shining with the light of 10 trillion suns, still ongoing right now, 10 billion light-years away. A 1 in a million event among active galaxies. If you mean the most total energy released in a single discrete event, it is the Ophiuchus eruption. A cavity 15 Milky Ways wide, carved by jets that burned for millions of years. 5 × 10 to the power of 61 ergs. Nothing else comes close. And if you mean the new frontier, the class of event that astronomers did not even have a name for until 2025, it is the extreme nuclear transients. the ENTs, events that are not supernovae, not ordinary tidal disruptions, not blazars. Something new. Massive black holes devouring massive stars and releasing energies that sit in a gap between anything we had previously categorized. What ties all four together is a single mechanism: a supermassive black hole consuming matter and converting that matter into energy with an efficiency that no other process in the universe can match. When matter falls toward a black hole, up to 42% of its mass can be converted to energy before it crosses the event horizon. For comparison, nuclear fusion converts less than 1%. Antimatter annihilation converts 100%, but requires antimatter, which barely exists in nature. Black hole accretion sits in between, using the most abundant fuel in the universe, ordinary gas and stars, and extracting energy from it with an efficiency that only total annihilation can beat. That is why the largest explosions since the Big Bang are not nuclear. They are gravitational. The most violent events in the universe are powered by the simplest force: matter falling. Here is what stays with me. Every one of these events was discovered by reading light. Faint signals, collected by telescopes, analyzed by researchers who noticed something that did not fit the pattern. The BOAT blinded our detectors for minutes. Scary Barbie hid in survey data for 2 years before anyone noticed. Superman was dismissed as a blazar for 5 years. The Ophiuchus cavity was spotted in 2016 and dismissed as too large to be real. The most violent events in the universe do not announce themselves. They whisper. And we have only been listening carefully for about 20 years. The Vera Rubin Observatory is coming online now, surveying the entire sky every few nights. It will see transients we have no categories for yet, events that make the ENTs look modest. We used to think space was quiet. Now we know it is not. And the biggest detonations may be the ones we have not heard yet. In our next video, we are going to look at the one type of cosmic explosion that could actually reach all of us: gamma-ray bursts, the sniper shots of the cosmos, and what would happen if one were aimed at Earth. Subscribe so you do not miss it.